Hello everyone, it's my pleasure to present my research. I'm Eunjin Jang and Professor Chao Ye is my supervisor. And today I'm going to talk about my research, energetic ion dynamics near the cusp region of Mercury. Before I begin, I will briefly tell you about my personal information. My name is Eunjin Jang and I'm from Korea. I have studied abroad in China since I was a child. I graduated from Peking University in 2018, and I major in space physics. Now, I'm a master's student from Institute of Space Physics and Applied Technology at Peking University. Here are the contents of my presentation for today. First, I will talk about the magnetosphere. The Earth's magnetosphere is the region of space surrounding Earth that is controlled by the Earth's magnetic field. The Earth's magnetic field is represented by a field of a magnetic dipole. The strength of the magnetic field on the surface is nearly 30,000 nanotesla at the equator. The magnetosphere extends several tens to thousands of kilometers into space. On the day side of Earth, the magnetic field is significantly compressed by the solar wind. The distance from surface to magnetopause is approximately 10 Earth radius, and the magnetosphere could protect the Earth from the charged particle of the solar wind. And Mercury is the closest planet to the Sun in the solar system. Mercury also have the similar features like Earth. Mercury is the only inner planet with a significant magnetic field except for Earth. The strength of magnetic field is 200 nanotesla at the equator, because the Mercury's magnetic field is weak and the solar wind compression is relatively strong, so the size of magnetosphere is much smaller than Earth. The mean distance from the internal dipole to the Mercury's magnetopause is only 1.5 Mercury radius. In this study, we mainly discussed about the cusp region of Mercury. Before we started, we firstly talk about the study of the Earth's cusp region. Many preceding studies have suggested that the cusp is observed to contain an off-equatorial magnetic minimum region. Here is a figure of closed magnetic field line. It shows that there are the two magnetic minimum regions, and the two minimum regions represented northern cusp and southern cusp, respectively. And the right figure shows the result of simulations, and it suggested that the energetic particles are trapped by the field minimum plane near the northern cusp region. According to previous study, there also are the off-equator magnetic minimum points in Mercury. In this figure, the blue region shows the minimum magnetic field region. In Mercury's magnetosphere, this region fills the closed field line on the day side. Because the energetic particles in the cusp region are affected by a mirror force that always pointed to the magnetic minimum, so it could form a trapped region near the cusp. So, The purpose of our study is to identify under what conditions this energetic proton can be trapped near the cusp region of Mercury. Through observation and simulations, we studied the dynamic process of Mercury's energetic ions under different solar activity conditions. And to compare, we choose the two different conditions of case. And this is the data what we used in this study. We used the magnetometers and the fast imaging plasma spectrometer instruments data from MESSENGER. And to simulate the test particles, we used the Mercury magnetic field model KT-17. And this is the result of our study. For case 1, we choose the January 25th, 2014 event. As shown in this slide, MESSENGER moved from night side to day side, and we could find that the flux of 1 to 10 keV proton was largely enhanced when the MESSENGER entered near the cusp region. It means that there are the high latitude trapping region. To modeling, we check the condition of magnetic field of Mercury. As the figure shown, the modeled magnetic field are quite similar to observed field. And we get the DI index and RSS. DI is the magnetic disturbance index, and in here DI is 90. And RSS is the standoff distance of Mercury magnetopause at the subsolar point, and in here is a 1.33 Mercury radius. And it indicated that the KT-17 model with DI 90 will represent the magnetic field configurations of Mercury during this period. And the magnitude of this index shows that the magnetosphere of Mercury is highly compressed on the day side. And to modeling, we check the condition of magnetic field of Mercury. As the figure shown, the modeled magnetic fields are quite similar to the observed field. And we get the two index. The one is DI index. DI is the magnetic disturbance index. And in here, DI is 90. And RSS is the standoff distance of Mercury's magnetopause at the subsolar point. And RSS is 1.33 Mercury radius. It indicated that KT-17 model with DI 90 will represent the magnetic field configurations of Mercury during this period. And the magnitude of this index shows that the magnetosphere of Mercury is highly compressed on the day side. Using this index, we simulated the test particle trajectory. And it is the trajectory of different energy protons. All of them are trapped in the high latitude region. And for case 2 is the event of June 4th, 2013. In this case, messenger moved from day side to night side. And we also found that there is no trapped region near the cusp region. And using the same method, we got the DI index is 0 and RSS is 1.51 Mercury radius. In this time, the magnetopause is further out than case 1. And also using same energy range of proton and using same method, we simulated the energy particles trajectory. And it shows that energetic particles cannot be trapped in high latitude region. Now, I'd like to sum up my presentation with the following observations. Due to the strong local magnetic field minimum, the energetic particles can be bounced between the local mirror points and get trapped in the high latitude trapping region of Mercury during magnetic disturbance. But when the magnetosphere is less compressed during relatively quiet time, the energetic particles cannot be trapped and they are lost to the interplanetary space or the surface of Mercury. And this is the reference of this presentation. And the more detail of this study, you can see my paper of 2020. For my future work, because I previously studied about the energetic ion dynamics in Mercury, so now I'm trying to study the energetic ion dynamics in Earth's magnetosphere. I will focus on substorms contribution on ring currents, especially the non-storm time super substorms case. And now I'm studying the case of interplanetary shock-induced substorms. And I got a preliminary result through the statistical analysis. Lastly, it is the last semester before graduation, so I thought about my future plan. After graduation, I want to participate in work related to my major. And if I have a chance, I would like to continue study for PhD. So that's all I have prepared today. Thank you for listening.